In this video we will be discussing key concepts of plane curves, space curves and surfaces all in Euclidean space. A curve is generally speaking similar to a line, however it is not required to be straight. A plane curve is a curve in two-dimensional Euclidean space. The curve gamma is a mapping on the interval alpha beta to R2. An example of a plane curve is cos t, cos t, cos t, sin t. Now when working with curves it is important to find out properties about these curves. And one of these is whether a curve is regular. A regular curve is a curve where the speed is never vanishing. That means the derivative of gamma of t is never equal to 0. As we can see for our example curve, gamma of t is never equal to 0 for the domain of t, that is the whole real line. Therefore, our curve gamma is regular.
Speed reparameterization. As this curve is regular, there exists a unit speed reparameterization. To reparameterize by unit speed, we need to do the following 4 steps. Checking gamma prime of t is not equal to 0 for all t which is the element of alpha and beta. For example, verifying the length of gamma prime of t is not equal to 0. Below is our back example of this. Secondly, computing the arc length function of s of t between t and t0 of the length of gamma prime of u du for a convenient t0 which is the element of the interval. Also below is our back example of the arc length function. As you can see, when inputting our length of gamma prime of u, this is an elliptic integral which we cannot integrate, so therefore we cannot proceed with the following steps of our unit speed reparameterization. If our integral is not elliptic, our third step would be computing the inverse of s of t. Our fourth step would be composing gamma with the inverse, and our last step would be verifying that gamma pseudo prime of t is equal to 1.
The curvature is how much a curve curves. It's defined by the following function. The curvature for our curve is the sine curvature describes the curvature of a curve in relation to the normal, and this is defined as the sine curvature for our curve is defined by the fundamental theorem of plane curves states that you can find a unique curve up to rigid motion given a smooth function k. In this case, we have calculated our sine curvature from previous, so we can find a geometric representation of the curve.
Now we are going to talk about space curves. A space curve is just a curve in R3. An example of a space curve is: firstly, we check if the curve is regular. We can clearly see that gamma prime does not equal to 0, therefore it is regular. As the curve is regular, we can find a unit speed parameterization that is given by to work out the curvature of a unit speed curve, we use the following formula. However, in this case it's easier to use the non-parameterized version and use the following formula. Therefore, the curvature for our curve is defined as the torsion of a curve measures how sharply it is twisting out of the plane of curvature. The formula for calculating torsion is given by the following formula, and therefore the torsion of our curve is given by the fundamental theorem of space curves, we know that the curvature and torsion define a unique curve up to rigid motion. The geometric representation is given by from one angle, the curve looks the same as the plane curve, however it has a third dimension, causing it to be a space curve.
Now it's time to move on to surfaces. We have a surface patch if a mapping X is a homomorphism from a subset U to the surface S. That is, x is bijective and x and x inverse are continuous. An example of a surface patch is as follows.
The first fundamental form is given by three coefficients E, F and G. E is given by the inner product of xu, xu, F is given by xu, xv, and G is given by xv, xv, which is shown on the slide. Now given this, we can put into a matrix I. The first fundamental form calculates lengths, angles, and the area of a surface. The second fundamental form is given by two steps. First of all, you have to work out the gas mass. The definition is shown below. Similar to the first fundamental form, you have to work out three coefficients, little e, little f and little g. E is given by the inner product of xuu and nx. Little f is given by the inner product of xuv, nx. Little g is given by the inner product of xvv and nx. The matrix of these coefficients are given below. The second fundamental form shows how curved a surface is.
The mean curvature is defined by, and the Gaussian curvature is defined by. We can visualize both mean and Gaussian curvature. As we can see, the mean curvature is equal to 0 and therefore is a plane.
You can also calculate the normal and geodesic curvatures of curves on the surface. The formulas for these are given below. The geometric interpretation of the surface is as shown. The mean curvature of our surface is 0, so we know our surface is in fact a minimal surface. Interestingly enough, minimal surfaces are formed in nature by soap films. Minimal surface theory first originated with Lagrange in 1762, and now nearly all is known about these types of surfaces. We hope you enjoyed our video.